Morning. My name is Joshua Davey, and I'll be speaking about my work um, examining the rheological studies of chocolate to optimize 3D printing settings. Um, so why chocolate, right? Chocolate is a viscoelastic material, meaning it behaves with elastic properties like a solid and viscous properties like a liquid. What gives it this ability is the cocoa butter inside the chocolate. Cocoa butter is a polymorphic material, meaning that it can assume many different shapes and forms. We get these shapes and forms through the process of tempering the chocolate. When we do, the temperature and the flow properties are going to change with each and every form, and they'll continue to be affected depending on the percentage of cacao content. So how can we work with this material that with all these different properties and all these different fluctuations, right? There's just too many factors to keep track of. So what did we actually do? We ended up using Ghirardelli dark wafers, which are nice because they have 60% cacao content and are pre-tempered. So we don't have to figure out how to temper. We ended up using an Ender 3 Pro with a food extruder extra add-on. And then we used an Anton-Par rheometer to get all of our real data. So what we did in the beginning was we took the chocolate, we loaded it into a tube, we melted that down, and we just stuck it in the machine and tried to print something. But the issue was that it was taking too long for the material to solidify, so we just couldn't print with it, and we were wasting a bunch of material. It wasn't until we conducted rheological measurements on it that we discovered that our preparation method was flawed. It just couldn't work. What we found was that once we had taken the chocolate material and pushed it past that 40 degrees Celsius mark, it just wasn't solidifying anymore. It had lost its ability to form crystalline structure. And so what we did afterwards is we instead very, very slowly brought the chocolate up to about a 32-degree mark and just let it sit there, let it melt slowly. This immediately produced better printing conditions for us. But what does any of this actually look like? Well, on this chart on the left, we have a temperature versus complex modulus graph, which is broken up into the storage modulus and the loss modulus. The storage modulus is the material's ability to build up and collect elastic energy. And the loss modulus is this material's ability to lose it. Basically, it determines, is it behaving more like a solid? Is it behaving more like a liquid? And so on this chart on the left, we see two tests. One where we took the material from 27 degrees to 33, and one from 27 to 40. Now, you can see very clearly that the complex modulus for the 27 to 33 test is way, way higher than the 40. This kind of tells us that once it's reached that 40-degree temperature, the polymorphic ability of the cocoa butter to form a stable crystalline structure has broken down. It is still, there's some structure, but it's not nearly enough to store as much elastic potential energy as the other. What this graph kind of tells us as far as optimizing our settings for printing is it kind of gives us a good working temperature range, a good place where we can get our chocolate to and hold it there. The chart on the right is a shear rate versus viscosity graph displaying 4 different constant temperatures at a slowly ramping shear rate. This chart is great for us because it shows us how the chocolate is going to behave under a variety of different conditions, right? This chart is great for telling us a good nozzle temp, because as we apply pressure to the material using a piston kind of pushing it down behind it, we get an increasing shear rate as this material flows into the nozzle. And so if the temperature is too low or the shear rate isn't high enough, the material might become too viscous and may clog up the nozzle, or it might become too flowing, right? It'll just ooze out. So this chart on the right gives us a good indication to find a nice ideal working nozzle temperature. Now, all of this is very, very critical with temperature, right? If we have it too high, we get these little mushy, like wide prints. If we get it too cold, we get these weak, like stringy, thin walls. If we can get it right, ideally we can get this nice clean line box in the middle. We were only able to get that once. I'm not quite sure. We've been trying to get back to this ever since, but we got a really nice solid model here where we were kind of in the middle. In conclusion, studying the rheology of the chocolate allowed us to understand what was going on with our prints, and it shed light on our faulty preparation methods. Using these measurements, we were able to find a good working temperature from around 29 to 32 degrees Celsius. And we now know that if we raise it too high, the crystalline structure within the material will begin to break down, making it practically useless. The next couple steps for this would be to start examining like shear stress thresholds to see how fast we can have this material moving before it starts to break. And that'll give us a good indication of printing speeds. We can also continue to look into the crystallites, their structures, how they form, how they break down, how quick can they form, how quick can they break down. And overall, this was quite a tasty project, and I look forward to continuing to work on it.